Welcome to EDU World Space.
Barnard star is a dwarf star that's fairly near our sun. And because it is nearby, we can actually measure its distance using something called parallax. Okay, so parallax actually is a measurement of how the star moves against the backdrop of stars between 6 months of observation. And the distance can be found as the inverse of that parallax in arc seconds, with the distance being in parsecs. Okay, so certainly we can figure out that distance, and it comes out to be 1.8. We'll give it a few more decimal places. The other thing that we can measure is the proper motion, so-called proper motion, which is how much the star appears to move across our celestial sphere in a short period. So it's separate from the parallax, which is the motion against the backdrop of stars due to the Earth's motion. So the proper motion is given by mu. And what we are going to be trying to find here is, let me draw the Earth in here. And we have Barnard star, which I will not draw according to scale. But there are two types of motion. There is motion to and away from the Earth called radial velocity. Okay, and we're after meters per second. There's also what is called transverse motion, which is perpendicular to that line of sight, and that is related to the proper motion. We'll call that v theta. So we basically have some information here, and we want to find these two velocities from the information given. So as you may have realized by my writing down the hydrogen alpha line, is that the radial velocity is found from the Doppler effect on light, which comes about because the observed wavelength of a particular narrow line is not the same as the wavelength you would measure in a lab. And that formula gives us the observed wavelength of the hydrogen alpha minus the wavelength that you would observe if the source was in a lab. So we'll call that lab rest or lambda rest. That difference over the rest wavelength is the radial velocity divided by c. That's an approximation for low speeds. We don't expect Barnard's star to be moving relativistically. So let's write down what the hydrogen alpha line wavelength is at rest. And we'll need quite a few sig figs. Okay, so if we put these into the formula and we use the speed of light, I like to use it with a few sig figs. So first of all, we get v over c, the radial velocity over c, is the difference in wavelength divided by the rest wavelength. Let me check that number out real quick. And we get, so yeah, it's definitely a low speed. And then if we multiply that by the speed of light, we get roughly, and that's negative minus 112 kilometers per second. That seems like a reasonable value. And the negative, by the way, the negative just means that the star is coming towards us. And we don't know from the proper motion whether the star is moving east or west or north or south. So we won't worry too much about that. That's just the transverse motion. Okay, for the transverse motion, we're going to think about the translation of that motion into an angular arc that it's moving through in a certain amount of time. And to convert that into a linear velocity, we need to multiply by the distance. Okay, so the idea is that we've measured a little bit of arc length that the star has moved through. And so S is equal to d times delta theta. And it's actually a delta S. And so delta S over delta T is the v theta. And of course, if that motion is small enough, we can think about infinitesimal amounts. Okay, and we did find the D is 1.8215 parsecs. We do want to get ourselves into kilometers per second. So 1.8215 parsecs times, let's convert that into kilometers. A lot of kilometers in a parsec. But that is a well-known conversion factor. Okay, so the distance, if we convert it, and we're going to have to convert some other things to get this into the proper units. Okay, so the delta theta over delta t is, we're going to have to convert our arc seconds into radians. And let me take this a little bit at a time so it doesn't look quite so jumbled up. But yeah, units can be a real nightmare. So yeah, we have the angular motion very accurately. And we're going to convert that to radians. So there are 60 squared arc seconds in a degree. Let me write this out a little bit cleaner. 1 degree is 60 squared. And I should put that up there. And then there are pi radians in 180 degrees. Okay, so we'll have to take that number 10.3577, and divide by 60 squared, multiply by pi, divide by 180. And let's see. We get 4.848 times 10 to the minus 6 radians. And the delta t is 1 year. We want to turn that into seconds. So there are 365 days per year and 86,400 seconds per day, which you can get by taking 24 hours and turning that into seconds. Yeah. Okay, so we can finally find our transverse velocity by taking our delta theta and dividing by our delta t and multiplying by the distance. And that should give us kilometers per second. Because radians are really unitless, they can be dropped, whereas arc seconds are an arbitrary angular unit. Let me check my numbers. Okay. Again, let me check my numbers. And I forgot to multiply by, yes, okay. My apologies. All that converting. We still need the proper motion in there. Which was the 10.3577. And the rest are just conversion factors. Okay, and that winds up to give us 89.6 kilometers per second. Okay, so yeah, conversion was a little bit crazy with that. So we do now have our two velocities, our radial velocity and our transverse velocity. And if we wanted to find the total, what's called space speed through space, that Barnard star is moving in, we can add those two numbers in quadrature because they are at right angles to each other. So you can think about them as components of a vector. And when you do that, it's a little bit over the 112. It's 144 kilometers per second.